Zeal Education Society, redefining excellence.
Welcome back. So earlier we talked about some characteristics of our parallel programs, and scaling was one of the characteristics which we discussed earlier. Let's continue with that topic. So consider a given problem size, that is the value of your TS remains constant, because what do you mean by TS? TS is nothing but the time required to start a message. When you talk about time required to start a message, it comprises of many things. First, the amount of time which is required to fetch the memory and to decode it and to make it prepare, or in computer terms you can say that to gather it in one slot and send it. This and many more. So your startup time for a message, it itself consists of a huge number of tasks which are supposed to be carried out. For this same reason, it is said that if for a given problem size, if you divide a message into many parts, that is, if you make it fine granular, then your startup time for every message will govern the performance of your parallel system. And if you have fewer partitions for a data, then, or in other words, you can say that it is a coarse granular data, then the time startup time for every message or a part of that message would be small as compared to startup time of fine granuled data. So it is always said that you should have neither fine granular nor to an optimum coarse granular, but have a balance of both, so that your startup time also remains pretty much constant, and that will give a boost to your performance. And in fact, that will give a boost for your computations, your communication time, and eventually your performance of your parallel system will be better. So we say that for a given problem size, so if your problem size is fixed, as I said you, the startup time will also remain constant. Let's take an example for it. I have 10 numbers, random numbers, random two digit numbers, which are supposed to be sorted by using two processing elements. Say I am using a fine granularity into it. That means 5 elements are assigned to one processing element, or 5 numbers are assigned to one processing element, and second 5 numbers are assigned to second processing element. When you say 5 numbers are assigned to every processing element, in total we have 2 processing elements and 10 random numbers which are supposed to be sorted. Startup time for one partition which has 10 numbers in it would be less as compared to, let's take another example, that I have 10 processing elements and I have 10 random numbers, again 2 digit numbers, which are supposed to be sorted. Now in second case, fine granularity, I have one message, or sorry, one number which is assigned to one processing element. So startup time for initiating one computation of one number would be higher as compared to startup time for computation of or sorting a 5-digit number. Sorry, so 5 numbers. So over here you can compare if my 5 numbers on one processing elements, whereas I am supposed to talk about sorting locally. First I need to sort those 5 numbers locally on processing elements, 1 and 2 both, right? And then I need to combine it. But in the second case, fine granularity, there I need to merge two numbers, that is two processing elements numbers. I need to merge it, sort it, then third sort it, then fourth sort it, and then fifth sort it. Startup time is high, computation time is high for fine granularity. Okay, so this is eventually affecting your processing time. So as we can increase the number of processing elements, so we are talking about scalability, right? So if your problem size, say consider that I have a fixed given problem size and I can increase the number of processing elements. So T0 also increases. What is T0? T0 is nothing, it is an overall time, sorry, overhead time. Okay, so the overall efficiency of your parallel program goes pretty down because T0 increases, and consider that Ts remains constant. And this is the case for your for irrespective of any parallel programs which you are taking. Consider addition of two numbers, addition of numbers on processing elements. So we have earlier seen that the amount TP is nothing but the time required for parallel computation is equal to n by p plus 2 log p. S is nothing but your speed up, which is equal to n by p 2 log p, and E is equal to 1 upon 1 plus 2p log p of n. As seen in the figure over here, this figure specifies the plotting of the speed up for various input size. Okay, you have the speed up on the y-axis and the number of size or your problem size increases on the x-axis. So when you talk about this, speed up tends to saturate and efficiency tends to go down or drops as a consequence of your Amdahl's law. What it says is, effectively what it is said over here is, you can see over here for n is equal to 64. Okay, speed up was close to 5. For n is equal to 192, speed up was close to 10. For n is equal to 320, the speed up was close to 15. And for n is equal to 512, the speed up is nearly, not even nearly, in between 18 to 20, you can say. But an ideal line is shown over there, linear. As you increase your speed up, you are also gradually increasing your numbers. So it should give you a linear line. But that is not the case when you're talking about practical implementation. So when you talk about it, it affects your Amdahl's law dearly. Let's talk about some more scaling characteristics of parallel program. So total overhead function, that is T0, is a function of both problem size, that is TS, okay, and the number of processing elements. The In many cases, T0 grows sublinearly with respect to your TS, and in such cases the efficiency also increases if the problem size is increased, keeping the number of processing elements constant. But as you increase the number of processing elements, your efficiency goes down. So for such system, we can simultaneously increase the problem size and also the number of processors to keep your efficiency constant. And we all call this systems as your scalable systems. So you need to keep it in mind that as you increase your size or your problem size, you should keep on increasing the number of processing elements which are used to compute or perform computations on that problem size. If you maintain that balance of total numbers plus your processing elements which are added gradually, both are gradually increased, then you can have a constant efficiency of your system. And the systems which has this uh, nearly constant efficiency are called as scalable parallel systems. That's it. Thank you.
Zeal Education Society, redefining excellence.